The Sun is 1,000,000 times the size of Earth. It fuses 600 million tons of hydrogen every single second. And right now, as you're watching this, there is a hole in it. Not a crack, not a wound, a massive dark void in the Sun's outer atmosphere that stretches wider than 30 Earths lined up side by side. And from that void, a river of superheated plasma is screaming through space at over 500 miles per second, aimed directly at our planet. Then, on May 10th, 2024, a barrage from the Sun slammed into Earth's magnetic field and triggered the most extreme geomagnetic storm in over 2 decades. Aurora lit up the sky in Puerto Rico. GPS-guided tractors in Kansas veered off their planting rows. Satellites scattered like startled birds. And that was just a taste. To understand why the Sun keeps doing this, and what happens when the next one hits, we need to look at one of the most underrated features in our entire solar system. This is the story of coronal holes. If you pull up NASA's Solar Dynamics Observatory right now and look at the Sun through its 193 angstrom ultraviolet camera, you'll see something that looks genuinely unsettling. Most of the Sun glows bright, almost white-hot in these images. Active regions shimmer, loops of plasma arc across the surface like bridges made of fire. And then, right in the middle of all that chaos, there are these enormous dark patches. They look like somebody took an eraser to the Sun. Those dark patches are coronal holes. And despite how dramatic they look, they are not actually holes at all. They're regions where the Sun's magnetic field, instead of looping back down to the surface like it does everywhere else, opens straight up into space. Picture a magnetic archway collapsing into a highway. Where the loops hold plasma in place and keep the corona dense and hot, the open field lines let everything escape. The plasma just slides right out along those open magnetic highways and disappears into the solar system. Because so much material is leaving, coronal holes are cooler and far less dense than the surrounding corona. About 1 million degrees Kelvin compared to roughly 2 million degrees everywhere else. Less density means less ultraviolet light, which is why they show up as black voids in NASA's cameras. NOAA's Space Weather Prediction Center has a blunt way of describing them. Coronal holes appear dark because they are cooler, less dense regions than the surrounding plasma sitting on open, unipolar magnetic fields. Now, you might be wondering how something that looks like a wound on the Sun differs from all the other scary solar features you've heard about, because the Sun has plenty of those. Sunspots are dark patches too, but they sit on the visible surface and are caused by intense closed magnetic fields suppressing convection. They're cooler than their surroundings, sure, but they're a totally different animal. Solar flares are sudden explosions of electromagnetic radiation when magnetic field lines snap and reconnect. They last minutes. Coronal mass ejections are the heavy artillery, billion-ton clouds of magnetized plasma that can cross the Sun-to-Earth distance in as little as 15 hours. Coronal holes are none of those things. They are quiet. They are persistent. Some of them last for months, even years. They don't explode, they exhale. And what they exhale is the fast solar wind. Here's where things get wild. The stuff pouring out of coronal holes is a non-stop stream of charged particles, mostly protons and electrons with some helium nuclei mixed in, and it is traveling fast. The normal, slow solar wind drifting out of closed-loop regions near the Sun's equator moves at about 400 kilometers per second. The fast wind screaming out of coronal holes hits 500 to 800 kilometers per second. That is not a typo, by the way. We're talking about 1 million miles per hour. NASA's Parker Solar Probe has flown straight through this stuff. In June 2023, a team led by UC Berkeley physicist Stuart Bale published findings in the journal Nature, identifying the exact engine driving the fast wind. They traced it to magnetic reconnection happening inside funnel-shaped structures at the base of coronal holes. Tiny magnetic field lines are constantly snapping and reconnecting down there, and each reconnection event acts like a slingshot, flinging plasma outward along the open field lines. Meanwhile, the European Space Agency's Solar Orbiter caught something equally stunning. In 2023, Its extreme ultraviolet cameras spotted thousands of tiny plasma jets, called picoflare jets, firing off the floor of a coronal hole every 20 to 100 seconds. A team published in the journal Science describing how these jets produce enough heated plasma to sustain the entire solar wind. So the sun isn't gently leaking material. It's firing thousands of tiny plasma cannons every minute from the bottom of every coronal hole, and that material eventually reaches us. And this brings up one of the biggest unsolved mysteries in all of physics. The surface of the sun, the part you'd actually see if you looked at it, sits at about 5,800 degrees Kelvin. That's hot, obviously, but here's the problem. The corona, the wispy outer atmosphere floating above that surface, reaches 1 to 3 million degrees. That's hundreds of times hotter than the surface below it. Imagine walking away from a campfire and finding that the air 50 feet away is 1,000 times hotter than the flames. It makes no sense. Heat is supposed to flow from hot to cold, not the other way around. Scientists have been arguing about this coronal heating paradox for decades, and the picoflare jets and magnetic reconnection events that Parker and Solar Orbiter are discovering may finally be the answer, which, looking back, was either incredibly brave or incredibly stupid, depending on how much you trust a spacecraft built to survive 2,500 degree Fahrenheit temperatures. Parker chose brave. Now here's the thing about coronal holes that makes them uniquely important for us back on Earth. Unlike solar flares and coronal mass ejections, which erupt without warning, coronal holes are predictable. The sun rotates on its axis once every 27 days from our perspective. That's called a Carrington rotation, named after the British astronomer Richard Carrington. And because coronal holes can persist for months, their high-speed wind streams sweep across Earth on a regular 27-day schedule. Every time the sun completes a rotation, that same coronal hole swings back around and fires another blast at us. NOAA's forecasters actually use this predictability to their advantage. They run a model called Wang-Scheele-Arge, coupled with the Enlil heliospheric simulation, and it gives them 1 to 4 days of advance warning when a coronal hole stream is about to arrive. When the fast wind from a coronal hole catches up to the slower wind ahead of it, the collision creates what scientists call a co-rotating interaction region. It's basically a pileup of compressed plasma and magnetic field, and when that compressed front hits Earth's magnetosphere, it triggers a geomagnetic storm. These storms are usually moderate, G1 or G2 on NOAA's 5-level scale, but they are constant, and they are about to become the dominant form of space weather for the rest of this decade. Here's why. Coronal holes are most prominent during the declining phase of the sun's 11-year activity cycle. Solar cycle 25 hit its peak in October 2024. We are now on the downslope. That means fewer explosive flares and CMEs, but more coronal holes, bigger coronal holes, and more frequent high-speed wind streams aimed right at Earth's orbit. So what actually happens when a blast of solar wind hits our planet? NOAA rates geomagnetic storms on a scale from G1 to G5. G1 is minor. You might see some aurora dancing at high northern latitudes, and there could be weak fluctuations in power grids. No big deal. G3 is where things start getting uncomfortable. Voltage corrections become necessary in power systems, GPS accuracy degrades significantly, and the aurora pushes south to places like Illinois and Oregon. G5 is the nightmare scenario. NOAA's own documentation uses the phrase complete collapse or blackouts of power systems possible. Transformer damage, pipeline currents surging into the hundreds of amps. High-frequency radio communications may be impossible in many areas for 1 to 2 days. Aurora visible in Florida and southern Texas. The way this damage works is almost elegant in how destructive it is. When Earth's magnetic field gets hammered by a solar wind stream or a CME, the rapid fluctuations induce electric currents in any long conductor on the ground. Power lines, oil and gas pipelines, undersea communication cables. These geomagnetically induced currents flow through the grounded neutrals of extra-high voltage transformers and saturate the iron cores, essentially cooking the copper windings from the inside. Replacement transformers cost millions of dollars and take about 15 months to manufacture. You can't just Amazon Prime a new one. In the ionosphere, the storm warps electron density and causes GPS signals to scatter, a phenomenon called scintillation, Your phone might show you in a parking lot when you're actually on the highway. In low Earth orbit, the thermosphere heats up and expands like a balloon, dramatically increasing atmospheric drag on satellites. And on polar airline routes where aircraft depend on high-frequency radio because satellite coverage is thin, storms force expensive diversions. United Airlines told Congress that a single polar reroute during the 2003 storms cost them an extra 3,000 gallons of fuel and $10,000 in operating expenses. Delta's internal policy is straightforward. When space weather hits G3, polar routes close. If you're finding this fascinating, hit that subscribe button. We cover deep dives on space and science every week, and the next one is going to blow your mind. Now let's talk about what happens when these storms get truly extreme, because we've already seen it. March 13th, 1989. 2 coronal mass ejections from a massive sunspot region slammed into Earth's magnetosphere, driving the KP index to 9+ and the DST index to -589 nanoteslas. At 2:44 a.m. Eastern Time, protective relays on Hydro-Quebec's power grid started tripping. By 2:45 a.m., just 90 seconds later, the entire 21,500 megawatt grid had collapsed. 6 million people across the province of Quebec woke up to complete darkness. No heat, no lights, no electric stoves for morning coffee. The blackout lasted 9 hours. Aurora was visible as far south as Cuba and Florida. About 2,500 objects being tracked in orbit were temporarily lost because atmospheric drag had shifted their positions. Hydro-Quebec spent roughly $2 billion Canadian dollars over the following 6 years hardening its grid with capacitors, relays, and early warning systems so it would never happen again. 14 years later, the sun reminded everyone that 1989 was not a fluke. The Halloween storms of October and November 2003 were a barrage unlike anything the space age had seen. Active region 100486 unleashed an X-17 flare on October 28th, an X-10 the next day, and then on November 4th, a flare so powerful it broke the detectors. NASA's GOES satellites measured it at X-17.5 before their X-ray sensors saturated. Later analysis estimated the true strength was somewhere around X-28, possibly as high as X-45. That's the kind of number that makes astrophysicists cry. The damage was real. In Malmö, Sweden, a transformer failure blacked out roughly 50,000 customers. Japan's Adios 2 satellite was destroyed, a loss of about $640 million, plus NASA's $150 million Seawinds instrument that was riding on board. The FAA's Wide Area Augmentation System for GPS went offline for 30 hours. Astronauts on the International Space Station sheltered inside the Zvezda module to reduce their radiation exposure. Every polar airline route on the planet was diverted. But all of that, the Quebec blackout, the Halloween storms, all of it pales next to what happened on September 1st, 1859. That morning, British astronomer Richard Carrington was sketching sunspots at his private observatory when he witnessed something that had never been recorded before: 2 patches of intensely brilliant white light erupting across a sunspot group. He had just observed a solar flare with his naked eye. 18 hours later, Earth was consumed by the most violent geomagnetic storm in recorded history. The Aurora reached the equator. People in Hawaii, Colombia, the Caribbean, and Queensland, Australia, saw the sky light up in reds, greens, and purples so bright that miners in the Rocky Mountains got up and started cooking breakfast, convinced the sun had risen. Newspapers in the American Northeast were reportedly readable by the light of the Aurora alone. The world's 124,000 miles of telegraph lines went haywire. Operators received electric shocks. Sparks leapt from equipment and set paper on fire. And in one famous incident, telegraph operators on the Boston to Portland line disconnected their batteries entirely and kept transmitting messages using nothing but the electric current being generated by the Aurora itself. Now imagine that happening today. Not to 124,000 miles of telegraph wire, but to a planet with 8,000 Starlink satellites, undersea fiber optic cables carrying 99% of international internet traffic, GPS networks guiding aviation and agriculture and financial transactions, and power grids that haven't been designed to handle currents flowing backwards through their transformers. Lloyd's of London ran the numbers in 2013. Their report projected $600 billion to $2.6 trillion in U.S. economic losses alone from a Carrington-class event, with 20 to 40 million Americans losing power for anywhere from 2 weeks to 2 years. The National Academy of Sciences put first-year damages at $1 to $2 trillion, roughly 20 Hurricane Katrinas, with full recovery taking 4 to 10 years. Water distribution would fail within hours. Perishable food and medications would be gone within a day. Heating, sewage, phone networks, and fuel supply chains would follow in rapid succession. And here is the part that should genuinely concern you. We almost found out firsthand. On July 23, 2012, a CME erupted from the Sun at roughly 2,500 kilometers per second, which is Carrington-class speed. It blasted straight through the space where Earth had been just 1 week earlier. Instead, it slammed into NASA's Stereo A spacecraft, which recorded the whole thing. University of Colorado physicist Daniel Baker, who reconstructed the event, was blunt about it. If it had hit, he wrote, we would still be picking up the pieces. The model DST, if it had struck Earth, negative 1,182 nanoteslas, Carrington territory. Physicist Pete Riley calculated that there is roughly 12% chance of a Carrington-class event occurring in any given decade. So if the threat is real and the odds are not trivial, what are we actually doing about it? More than you might think. We now have a fleet of spacecraft watching the Sun from multiple angles, and the coverage is getting better every year. NASA's Solar Dynamics Observatory has been orbiting Earth since 2010, snapping 4,096 by 4,096 pixel images of the corona every 12 seconds. It's the workhorse that makes coronal holes visible in real time. Then there's the Parker Solar Probe, which on December 24, 2024, Christmas Eve, made history by flying within 3.8 million miles of the Sun's surface at a speed of 430,000 miles per hour. That makes it the fastest object humans have ever built, and the closest we've ever sent anything to a star. Its project scientist Noor Rawafi said the probe is braving one of the most extreme environments in space and exceeding all expectations. Parker's data confirmed the magnetic reconnection engine, driving the fast solar wind out of coronal holes. ESA and NASA's Solar Orbiter, launched in 2020, discovered tiny campfires flickering across the corona, and in March 2025, returned the first ever photographs of the Sun's poles from 17 degrees below the ecliptic plane. Those poles are where the largest coronal holes tend to live during solar minimum, and we've never been able to see them clearly until now. NASA's Punch constellation, 4 small satellites launched in March 2025, started producing 3D images of CMEs and solar wind structures in April. Its principal investigator, Craig DeForest, explained that Punch will track space storms in 3 dimensions as they approach the Earth, which is critical for forecasting. And in September 2025, NASA and NOAA launched the IMAP and SWFO-L1 spacecraft together to the Sun-Earth L1 Lagrange point, about 1 million miles toward the Sun. They are there to replace the aging ACE and DSCO-VR Sentinels that have been providing upstream solar wind data for decades. When a CME is inbound, these spacecraft give forecasters roughly 15 to 60 minutes of advance warning. That's not a lot, but it's enough time to put transformers into safe mode and redirect satellite operations if the warning system works. Looking further ahead, ESA plans to launch its Vigil mission in 2031 to the L5 point, which sits 60 degrees behind Earth in its orbit. From that vantage point, Vigil will give forecasters a side-angle view of incoming CMEs, something no current spacecraft can do. Right now, we can only see CMEs coming head-on, which makes it extremely difficult to judge their speed and magnetic orientation until they actually arrive. On the ground, the US passed the ProSwift Act in 2020, formalizing interagency coordination for space weather preparedness. The Federal Energy Regulatory Commission standard TPL 007 now requires grid operators to model and mitigate geomagnetic disturbance events. Hydro-Quebec's $2 billion hardening program after 1989 proved it can be done. The question is whether every other grid operator on the planet follows their lead before the next big one arrives, because the vulnerability keeps growing. SpaceX lost 38 brand new Starlink satellites in February 2022 to a geomagnetic storm that registered only G1 to G2, which is about as mild as storms get. The heated thermosphere increased drag so much that those satellites never reached their operational orbits and burned up on re-entry. There are now over 8,000 Starlinks in orbit, and every single one of them sits in the thermospheric danger zone. And then there's this. NASA's Artemis program plans to send astronauts beyond Earth's magnetic shield for the first time since Apollo. A solar particle event like the one that occurred in August 1972, which happened between Apollo 16 and Apollo 17 missions, would have been potentially lethal for anyone standing on the lunar surface. The timing of that miss was pure luck. Solar cycle 26 is expected to peak from 2035 to 2037. By then, our satellite constellations will be even larger, our grid dependencies even deeper, and our reliance on GPS even more total. The real question isn't whether the sun will throw something massive at us. The sun has been doing that for 4.6 billion years. The question is whether we'll be ready when it arrives, or whether the next Carrington event will catch 8 billion people who built their entire civilization on electronics that were never designed to survive a direct hit from a star. The sun has a hole in it. Something is pouring out. And right now, the only thing standing between that stream and everything you depend on is a magnetic field about as thick, proportionally, as the skin on an apple. If you want to see what happens when the sun's other weapons, solar flares and CMEs, are aimed directly at Earth, that video is on screen right now. I'll see you there.